Most crime scenes are preserved behind yellow tape, but this one was hidden beneath about 35 feet of tropical water and 20 feet of silty mud. A steel hull is a binary switch. If the metal bends one way, the event is an internal structural failure. If it bends the other way, it is an external act of war. For 12 years, the most famous shipwreck in the Western Hemisphere lay at the bottom of a foreign harbor, answering neither question definitively. The water held the truth hostage, and the mud obscured the mechanism of destruction. The United States Navy warship Maine died on February 15, 1898. The massive explosion shattered the forward third of the vessel and killed 266 of her crew. The sinking triggered a conflict that redrew the map of the world, ending the Spanish imperial presence in the Americas and establishing the United States as a global naval power. The war was fought on the assumption of a mine, but the physical proof remained buried in the harbor floor. The initial investigation in 1898 relied on divers working in zero visibility, feeling jagged steel edges with their hands and reporting their tactile impressions to a court of inquiry. There was no photographic evidence of the keel and no clear view of the hull plates that took the primary impact. By 1910, the wreck was no longer just a shrine or a political talking point. It had become a lethal navigational hazard in the center of Havana Harbor. The growing commerce of the port had to navigate around the twisted steel skeleton of the main mast and the bridgework which still broke the surface. The currents around the wreck were unpredictable, and the presence of unrecovered remains created a diplomatic and moral pressure that could not be ignored. The ambiguity of the sinking was toxic. As long as the ship remained in the mud, the validity of the war itself was open to debate. The United States Congress authorized a dual mission with a heavy burden of proof. The engineers were ordered to remove the hazard completely, recover the dead, and examine the wreck as thoroughly as possible. This required a level of forensic precision that standard salvage methods could not provide. If they used chains and pontoons to rip the hull from the suction of the mud, they would distort the steel even further. They would destroy the very evidence they were sent to find. The violence of a traditional lift would render the forensic conclusion void. The engineers facing this problem realized that the environment itself was the enemy. The same water and mud that had buried the proof were now guarding it. To solve the equation, they had to subtract the variable of the ocean. They decided that they would not bring the ship up to the surface. Instead, they would bring the surface down to the ship. They proposed an operation that blurred the line between marine salvage and civil excavation. They would not work underwater, they would force the harbor to retreat. The plan was audacious in its scale and simplicity. They intended to isolate the wreck from the Caribbean Sea entirely. They would build a wall around the ship, seal it against the pressure of the ocean, and pump the site dry. They would turn the harbor floor into a dry construction site under the open sky. Only then could they walk around the keel, photograph the damage, and dissect the ship plate by plate. The decision transformed the project from a recovery mission into a war against hydrostatic pressure. The target was identified, the funding was secured, and the strategy was set. The engineers prepared to build a fortress in the middle of the bay. Traditional salvage would have been fast, brutal, and final, but it would have ruined the proof. This job demanded a different kind of engineer. Army engineer Harley B. Ferguson of the United States Army Corps of Engineers took command of the project with a different philosophy. He did not view the ship as a heavy lift problem. He viewed the water as a civil excavation problem. His solution was to treat the middle of Havana Harbor as if it were a construction site on dry land that simply happened to be flooded. He initiated a plan for what he called a dry excavation. The goal was to build a watertight fence around the entire wreck site, then pump it empty from within. Engineers call it a cofferdam, a temporary enclosure that shuts out water and exposes the seabed. In shallow water with a solid rock bottom, a cofferdam is a simple, single wall. But the Maine rested in 35 feet of water on a foundation of soft, unstable mud. A single wall of steel would buckle instantly under the crushing weight of the Caribbean Sea. Ferguson needed a structure that relied on its own massive gravity to stay put. The design called for a massive elliptical fortress composed of 20 independent steel cylinders. Each cylinder measured 50 feet in diameter. These were not solid concrete silos poured in place. They were constructed from a relatively new industrial component known as interlocking sheet piling. These piles were long, vertical strips of steel with curled edges that locked together like a zipper. When driven into the mud, side by side, they formed a continuous sand-tight skin. The engineers would drive these piles to form the 20 giant circles, linking them together to create an unbreakable ring around the battleship. The physics dictating this design came down to water pressure, the relentless force exerted by a standing body of liquid. At the surface, the water adds no extra pressure. But for every foot of depth, the weight of the water above pushes harder against anything trying to hold it back. At the bottom of the Cofferdam, the ocean would be pushing inward with thousands of pounds of force per square foot. If the Cofferdam was empty, there would be no opposing force from the inside to push back. The steel walls alone were too thin to resist this crushing load. To counteract the water weight, Ferguson planned to pack each 50-foot cylinder with heavy dredged clay and rock. This fill would turn the thin steel shells into massive gravity pillars. The weight of the clay would pin the cylinders to the harbor floor, and the friction of the dirt inside would prevent the steel circle from deforming. The cylinders would act like 20 heavy boulders placed in a ring, too heavy for the ocean to shove aside. Once the ring was closed and the cylinders were filled, the pumps would start. As the water level inside dropped, the differential pressure would rise. The structure would have to endure the full lateral thrust of the harbor. If a single interlock failed or a cylinder shifted, the sea would rush back in, destroying the evidence and likely killing the men working on the exposed floor. The plan was theoretically perfect. It converted the fluid chaos of a salvage job into a static geometry problem. But the calculations assumed the harbor floor was strong enough to support the immense weight of the dam itself. The blueprints were drawn for solid earth, but the engineers were building on a layer of mystery that had already swallowed a battleship. The construction of the steel ring began with a rhythmic industrial violence that echoed across Havana Harbor. Steam hammers drove the interlocking sheets into the harbor floor one by one, stitching the water with vertical lines of iron. The scale of the material logistics was immense. The engineers drove about 3,200 steel sheet piles to form the perimeter. The piles themselves were massive, spliced together to reach lengths of 75 feet. They had to penetrate through the water, cut through the deep, soft mud, and bite into the harder clay substrate far below to find a secure foothold. As the 20 cylinders took shape, they stood like empty silos rising from the waves, innocent in appearance but structurally vulnerable. A hollow steel cylinder is fragile against the sea. To give them the mass required to fight the ocean, the engineers began to fill them with heavy dredged clay. This process introduced a new and dangerous force known as hoop tension. When wet earth is dumped into a tall container, it behaves like a heavy semi-fluid. It does not just sit still, it pushes outward against the walls that contain it with immense radial power. The weight of the fill tried to expand the cylinder, stretching the steel skin until the interlocks groaned under the stress. The sheets were under constant attack from the very material intended to make them strong. The engineers were building a chain where every link was being pulled to its breaking point simultaneously. The greater threat, however, came from the harbor floor itself. The stability of the dam relied on a geotechnical concept called passive earth pressure. For a heavy object to stand tall in soft soil, the ground at its base must provide lateral resistance. It must push back against the buried foot of the object to keep it from sliding or tilting. The engineers discovered that the upper layers of the Havana mud were not solid earth, but a gelatinous soup that offered almost no passive resistance. The heavy cylinders were not standing on a rigid foundation. They were balancing on a viscous fluid. During the filling phase, the geometry trap sprung. One of the massive cylinders began to move. It did not burst, it started to lean. The soft mud beneath the outer edge gave way, and the 50-foot tower tilted inward toward the wreck, threatening to topple completely. If it fell, it would crush the ship and flood the workspace, ending the project in a catastrophic failure. The site became a slow-motion crisis. The engineers watched their fortress turning into a submerged Tower of Pisa. They had to frantically adjust the fill levels and reinforce the leaning tower with bracing to arrest the movement. They forced the mud to submit through careful load management and sheer structural stubbornness. The cylinders were topped off, the interlocks held, and the ring was finally closed. The pumps were installed, and the dewatering began. As the water level inside the dam dropped, the internal support vanished. The cylinders groaned as they took the full weight of the Caribbean Sea on their outer faces. The leaks were plugged with cinders and sawdust sucked into the gaps by the pressure itself. Slowly, the dark water receded. The top of the main mast had always been visible, but now the twisted superstructure rose from the surface. Then the deck appeared. Finally, after 12 years in darkness, sunlight touched the mud of the harbor floor, revealing a landscape that had been hidden since the 19th century. The water level inside the steel walls dropped to minus 15 feet, transforming the bottom of Havana Harbor into a wet, gray moonscape. The pumps had won the battle against the ocean, and the interior of the Cofferdam was now a protected amphitheater of mud. The engineers and inspectors descended into the pit, walking where no human had stood without diving gear in centuries. They were not greeted by a ship. They were confronted with a tangled industrial ruin. The forward third of the vessel had effectively ceased to exist as a coherent structure. It was a chaotic jungle of twisted beams, shattered bulkheads, and unrecognizable plating half buried in the silt. The first task was to strip away the disguise. The mud had preserved the steel, but it also hid the story. Crews used high-pressure fire hoses to sluice away the thick clay that coated the wreckage. As the water jets blasted the sediment away, the brown slime gave way to the dull gray of painted steel and the red of rust. The skeleton of the ship began to emerge in high fidelity. This was the moment the entire operation had been built for. The Vreeland Board of Inquiry stepped onto the damp floor to read the metal. They were looking for a specific signature of violence. The investigation hinged on forensic geometry. The plates would tell them whether the blast came from within the hull or from the harbor itself. An internal detonation pushes steel outward. An external charge drives it inward, folding it against the frames. The bend would point them to the culprit. The investigators crawled through the labyrinth of the destroyed bow, mapping every distortion. They identified a specific keel plate, which they designated as Section 1. This heavy structural component was located near the frame, where the center of the explosion was calculated to be. The plate was not just torn, it was folded. The steel had been driven upward and inward into the vessel, displacing the keel structure from the bottom up. To the eyes of the 1911 board, it seemed like the smoking gun. They concluded that a large external charge had detonated under the ship, lifting the keel and triggering the secondary explosion of the forward magazines. Section 1 looked like vindication for the long-argued mine theory. The dry excavation had worked. It had provided the physical access necessary to touch the evidence and measure the angles of deformation. The ambiguity of the underwater surveys was replaced by the hard certainty of visible steel. The board officially recorded that the Maine had been destroyed by an external mine, a conclusion that would remain the Navy's official finding for decades. But the satisfaction of solving the mystery did not solve the physical problem. The engineers now stood on the bottom of a dry hole, surrounded by thousands of tons of scrap metal that had to be removed. The bow was a total loss, a shattered mass that could never float again. The stern, however, sat upright and relatively intact, separated from the devastation forward by a zone of absolute destruction. The mission had two objectives: find the truth and remove the wreck. The truth was found. Now Ferguson had to figure out how to resurrect the dead half of the ship and make it swim one last time. The engineers faced a stark naval architecture trade-off. The vessel lying on the harbor floor was no longer a single ship. It was two distinct entities joined by a twisted hinge of scrap metal. The forward third was a chaotic tangle of steel that had lost all structural integrity. It was simply heavy debris that could never be made watertight. The aft two-thirds, however, remained a ship. The hull plates were true, the frames were aligned, and the engines sat rusting but secure in their mounts. To save the stern, Ferguson had to amputate the bow. This process is known in salvage engineering as sectioning. It involves the deliberate severance of a ship's structure to separate buoyant sections from dead weight. The crews attacked the wreckage with cutting torches and pneumatic tools, slicing through the thick armored belt and the deck plating. They dismantled the destroyed bow piece by piece, lifting the fragments out of the cofferdam with cranes. The twisted evidence of the explosion was carried away, leaving the harbor floor bare forward of the midships line. What remained was the stern section, sitting upright in the mud, but it was missing its front wall. It was an open bucket that would sink the moment the water returned. To make the ship swim again, the engineers had to construct an artificial face for the vessel. They identified frame 41 as the surgery line. This structural rib ran across the width of the ship just aft of the damage zone. Here, they would build a massive barrier known as a false bulkhead. In a normal shipyard, a bulkhead is a steel wall integrated into the hull. In a salvage zone, a false bulkhead is a temporary patch built from whatever materials are available, designed to withstand the full pressure of the ocean for a single voyage. The construction of this wall was a feat of carpentry and masonry performed inside the steel shell. The engineers built the false bulkhead from heavy timber framing and thick planking across the open end of the ship at frame 41, braced back against the ship's internal structure. To make the barrier watertight, they sealed and backed its base and joints with concrete and cement mortar. They effectively turned the open-ended wreck into a sealed barge. The stern was now a closed volume capable of displacing water. With the bow removed and the bulkhead finished, the dry phase of the operation ended. The pumps were reversed. Sluice gates in the iron wall of the Cofferdam were cracked open, allowing the Caribbean Sea to filter back into the pit. The water rose slowly, creeping up the sides of the rusted hull. The engineers watched the draft marks on the stern. As the water level equalized with the harbor, the laws of buoyancy took over. The mud surrendered its grip. The stern section, sealed by its new wooden face, broke free from the bottom and lifted. It floated on its own, stable and upright. The Resurrection was partial but functional. After 12 years as a submerged tomb, the Maine rode quietly inside the steel ring of the Cofferdam, trapped like a model boat in a bathtub. The engineers had proven that the dry excavation could reveal the truth and reverse the sinking itself. Now they had to dismantle their own wall and open a gate, so the ship could leave its prison for the final time. On March 16, 1912, the final operational window opened. The sky over Havana was clear, and the water inside the harbor was calm. The United States Navy prepared to execute the final maneuver of a mission that had spanned 2 years of engineering labor and 14 years of political tension. The resurrected stern of the Maine was floating, but it was still a prisoner inside the steel geometry of the Cofferdam. To release the vessel, the engineers had reversed the construction process. They had pulled up the interlocking piles on the seaward side of the oval, breaking the ring and creating a narrow gate just wide enough for the hull to pass through. At the appointed hour, the tow lines were secured, a Navy tug took the strain, and the rusted hulk began to move. The ship that emerged from the steel cylinder was a ghost. It was stripped of its guns, its mast, and its upper works. It was a floating torso, ending abruptly at the wooden wall of frame 41. Yet it flew the stars and stripes from a temporary jury-rigged pole. As the vessel moved slowly into the main channel, the shoreline of Havana was lined with tens of thousands of silent spectators. The fortress guns of the harbor fired a salute, marking the exit of the ship that had brought an empire to its knees. The tow convoy headed out of the harbor, moving away from the shallow mud that had held the wreck for so long. They crossed the 3-mile limit into international waters, seeking the profound depths of the Florida Straits. The objective was to put the vessel beyond the reach of any future salvage, any future storms, and any future political exploitation. The engineers had designed the scuttling sequence to be fast and dignified. They had installed sea valves in the bottom of the hull, rigged to be opened from the deck. When the convoy reached the target coordinates, the tugs cast off the lines. The boarding party, composed of the engineers who had spent years fighting to float the ship, now boarded it to sink it. They opened the sea valves, allowing the ocean to flood the compartments they had worked so hard to seal. The men evacuated to the waiting escorts, and the final watch began. The stern section settled evenly at first, the water rising up the rusted freeboard. The physics of the second sinking were controlled and predictable, a stark contrast to the violent detonation of 1898. As the intake of water increased, the buoyancy failed. The bowless hull dipped forward. The wooden bulkhead at frame 41, which had held back the sea for the journey, submerged. The pressure increased on the timber, but the ship slipped beneath the surface before the wall could fail. The stern lifted high into the air, vertical for a moment, and then slid smoothly under the waves. There was no explosion, no debris, and no loss of life. The water churned white for a moment and then returned to blue. The Maine was gone. Back in the harbor, the legacy of the operation remained visible for a few more months. The engineers returned to the Cofferdam to extract the remaining steel piles. The cylinders were dismantled, the clay fill was dispersed, and the expensive interlocking sheets were pulled from the mud to be sold for other projects. The scar on the harbor floor was smoothed over by the currents. The Army Corps of Engineers had delivered what Congress demanded. The dead were recovered and sent to Arlington. The hazard that choked Havana Harbor was gone. And in a pit they had forced the sea to surrender, the evidence was finally exposed, enough for the 1911 board to close the case. The verdict of that board would stand for decades, enshrined in history books as the final word. Future generations of naval architects and blast analysts would return to the data Ferguson collected using his photographs and measurements to challenge the mine theory and propose an internal accident. But those debates belonged to the future. In 1912, the water was clear, the mud was empty, and the silence had finally returned to the bottom of Havana Harbor.